video is on the rules for differentiation. So we've learned the process for finding the definition or the derivative by definition, but fortunately a lot of the things that we do have a little more simplified way. So for different things you have on your notes pages, you have all the different rules. And so I'm just going to do examples for each one of those. And I'm going to go through it a little bit quickly so you can just hit pause if you need to, but most of them are pretty simple. So the first example is example 1, which is right after rule 1, which talks about derivative of a constant. Well, that should be pretty easy because if the function is a constant, then that means it's a horizontal line. So shouldn't be too shocking that the rule is if you take the derivative, that the derivative would be 0, because that's obviously the slope of the line. So the next examples have to do with the one that we will use tremendously, which is the power rule, and we will use this a lot. And so first example is f of x is x to the 5th. The power rule says take the power and multiply it in front, so move the power down, leave the function, lower the power by 1, and that's it. That's all there is to it. So it's a pretty simple rule, and we will use the rule constantly. All right, so let's do some more. So let's do example 3. So example 3, we have f of x equaling third root of x squared. Now notice that I'm using proper notation, and that's really important for you to do too. If I write the function, I say f of x. Once I do the derivative, I change it. Because here I'm going to have to rewrite f of x before I can do the derivative, because it's written as the third root, but I need a power. So I'm going to rewrite that as x to the power over root. So x to the 2/3. Now I can do f prime, and f prime is put the power in front and then leave the function and then lower the power by 1. Well, you should be able to do this in your head, but 2/3 minus 1, well, 1 in thirds is 3/3, so 2/3 minus 3/3 is negative 1/3. And you would just leave that answer exactly as it is, because depending on what you need to do with it next, we don't know whether we want that to be back as a radical or anything, so just leave it. That's the answer. All right, so let's look at example 4. So example 4, again, we have f of x, and we have 1 over x to the 4th. So f prime of x, well, I can't really do f prime yet. I need to rewrite f of x because I have a quotient here, and right now I don't have another way to do this. I only know how to do powers and how to do constants. So I need to rewrite this as a power, and that's your x to the negative 4. Now I can do f prime, and f prime is power in front, leave the function, and lower the power by 1. So be careful here. We're subtracting 1, and so you're going to get negative 5. Alternately, you could write that negative 4 over x to the 5th. But again, just remember that we're generally going to either take this and do something with it or use it for match an answer or something like that. And so we want to be really careful to leave the answers and don't overdo it when we simplify. Kind of look at where we're going with it before we decide what else to do. All right, so the next rule that's written there before you get to example 5 talks about if you have a constant in front. And so the derivative of a constant times u is going to be just to take the constant times the derivative, okay? Now we're going to use lots of different notations here, and that's good. We need to get used to it because there's a lot of ways to write derivatives. So this question says find dy dx. Well, it's still asking me to find the derivative. It's just a different notation. So if y is 5 times x to the 7th, well, the rule just says you're going to just multiply by that constant when you're done. So most people just go ahead and think to themselves, okay, it's 7 times 5, so it's 35, and then leave your function and then lower the power by 1. And so it's 35x to the 6th. All right, let's do the next one. Example 6. We have g of x equals 4 over 5x to the third, and we want to find g prime. Well, first I need to rewrite g of x because, again, I need a power. And be really careful here. Remember that that cubed is only with x, not with the 5. So you have 4/5 x to the negative 3 to get that power out of the bottom. Now you can apply the rule, and we have g prime of x, and you're going to multiply. So again, if you need to, over to the side in a little scratch area, do your 4/5 times negative 3 so that you can see what you get. And you're going to get negative 12/5 x, and then you're lowering the power by 1, so that's negative 3 minus 1, so that makes negative 4. And then again, there could be other ways to write it, but we're just going to leave it until we know what we're doing with it. Okay, next property is sum or difference. Well, luckily, with adding and subtracting, we can just do everything separately and just work it all the way across. And that's what the rule says, that you can just do them all and then get the subtraction, or add or subtract them after you're done. So that makes it really nice. So we have x cubed plus 4x squared minus 2x plus 7. This is your example 7, and it says find y prime. Yet another way to write the derivative. So y prime is a way. So we have dy dx, we have f prime, we have y prime. So get used to all of those. So the derivative, we just take the power in front and we just work left to right. So power in front is 3, leave the x, lower the power by 1, plus 2 times 4, which is 8x, lower the power by 1, that's a 1, and then minus 2. If you're doing the derivative of a constant times x, it's just the constant. And then the derivative of the constant itself plus 7, that derivative is 0. And there you go. So let's do example 8. So here we have g of x equals 3 over negative 2x to the fourth minus x over 2 plus 1/4, and we want to find g prime. Well, before we find g prime, we're going to have to do a little rewriting of g because of this first term here, because we don't have a rule yet to deal with having a quotient. Well, for our purposes now, we're going to have to multiply out that denominator, or get rid of that exponent has to get applied, I should say. We're not really multiplying it out as much as we're applying the exponent, because I need to get the number separated from the x. So you're going to have 3 over, it's negative 2 to the fourth, which would be 16, because that's negative 2 times negative 2 times negative 2 times negative 2. And then you're going to have x to the fourth. And then still just leave these minus x over 2 plus 1/4. Well, we can't quite do the derivative yet because we have x to the fourth in the bottom. So leave the number, make it 3/16 x to the negative 4. And then minus x over 2 plus 1/4. And then you're just going to, now that we've rewritten it, it's really easy to find g prime of x. We just go through and do our derivative. So we take negative 4 times 3/16. Again, over here to the side, if you're not sure what to do, go write it down. 3/16 times negative 4. Don't sit and stare at it. Try to draw in the air. Just write it down. Divide that out, and so you get negative 3/4. So we have negative 3/4 x, and then we lower the power by 1. So we had x to the negative 4. We put the negative 4 in front, and now we lower by 1, and we get negative 5. Now, when we get to this next term, realize that that's the same as just negative 1/2 x. So negative x over 2 is the same thing as just saying negative 1/2 x. So this derivative is just negative 1/2. And then when you get here to the constant, that derivative is 0. And so now we have our answer. So this is g prime. Okay, let's go to another example. So let's go to example 9. Now this example goes a little further, says find the equation of the tangent line if we have this function. And we want to find the tangent line at x equals 2. So the first thing your mind should think is, I need to write an equation of a line. To write an equation of a line, I need the slope and I need a point. Well, where do we get the slope? Well, we find the derivative. So find the derivative. That will give you the equation that will give you all the slopes of all the tangent lines at the various points. You can use that to find your slope. Then you need to find a point and write your equation. So if we do f prime here, we should be able to do these pretty quick now. That's 12x squared minus 6. If we plug in 2, we want to find the tangent line at 2, so we want to plug in 2 in order to find what is the slope at that point. So if we plug in 2, we'll have 12 times 2 squared. So 2 squared is 4 times 12 is 48 minus 6, and so we're getting 42. We also need a point. Notice again my proper notation. This is f prime. That's the slope. F of 2 is going to just give me the point. I know x is 2, but I don't know the y that goes with it. So I have to plug 2 into f to figure out what it is. So 2 cubed is 8 times 4 is 32 minus 12 plus 5. So we're going to get 20 plus 5 or 25. It says write an equation. If you see write an equation, you use point slope form. Y minus the y value of my point. I just found the y value. It's 25 equals the slope. Well, f prime evaluated at a number is the slope. So 42 times x minus the x value, which was 2. And then I'm done, and I just stop there. Because remember, we don't want to do anything else because it just said an equation. It didn't say put it in slope-intercept form or anything, so just leave it just like it is. Okay, let's do example 10. So example 10, we have h of x equals x squared plus 1 times 2x minus 5, and we want to find h prime. Well, right now, we don't know how to do a product. We're getting ready to learn the product rule, but since we don't know the product rule yet, we're going to have to multiply this out and see what we get. So we get 2x cubed minus 5x squared plus 2x minus 5. Now if we find h prime of x, now we just use the power rule. So that's 6x squared minus 10x plus 2. Now I'm going to skip example 11. It's pretty simple. It just has different variables in it. But I'm going to look at example 12. So example 12 is saying, okay, well, let's figure out whether sum and difference, we can just do them all separately and then add or subtract when we're done. So we want to find out if this works for products. So we're going to take this example, and this is another way to write find the derivative. So we're going to take the derivative by multiplying it together first and then doing the derivative, which is the proper way to do it. And then we're going to do it by seeing if we can just take the derivative of each part separately and multiply the answer. So first, let me rewrite and do it the way you're supposed to do it, which is multiply this out. We get 3x cubed. And now do the derivative. We multiply our powers, lower the power by 1. So the correct answer is 9x squared. So here is what we're going to try. We're going to say, okay, I think that you can do, maybe somebody thinks, oh no, you can just do each derivative separately and then multiply the answer. So let's try that. So first derivative would be 2x, second derivative would be 3, and that gives you 6x. Well, 6x certainly doesn't equal 9x squared, so we've just shown that in fact that's not the case. So the product rule is what we need to use to cover products. And here's how the rule goes. So the rule for products is that if we take the derivative of two functions that are being multiplied. Now this can apply for more than two functions, but we'll get to that much later. It gets a little confusing. It's going to be the first times the derivative of the second plus the second times the derivative of the first. It does you good to learn that with those words. So I would hit pause and I would write those words down and fill that in. So it's first times derivative of the second plus the second times the derivative of the first. So let's go and do this example, example 13. And we're going to do it two ways. We're going to do this example with the product rule, or without the product rule and with the product rule. So as I copy this off my paper, I'm going to go ahead and change that x, the square root of x, to x to the 1/2, because we know that we need powers, right? Because we have power rule. So first let's say, okay, I don't have a product rule. I'm just going to go ahead and distribute all of this and use FOIL and get one term and then find the derivative. So we have 15x cubed minus 21 plus 10x to the, well, you're multiplying x to the 1/2 times x cubed, which means we add exponents. 3 is 6 over 2 in halves, so we're going to get 7 halves. And then we'll have minus 14x to the 1/2. And all I did there was FOIL. Hit pause and go back and take your time and make sure you understand that. That's y. Now let's find dy dx. So here we would get 45x squared, a constant. This right here will give me 0. Then I need to do 7 halves times 10. That would be 70 over 2, or 35x. I need to lower the power by 1. So 1 in halves is 2 halves. 7 halves minus 2 halves, 5 halves. Minus a half times 14 is 7x. And then 1/2 minus 1 is negative 1/2. So this is dy dx. Now we're going to use, so this is the correct answer. And now we're going to use the product rule and do the same thing. So let me rewrite y again and use the product rule and see if we get the same answer. So now the rule says take the first function, 3 plus 2x squared, times the derivative of the second. Well, this is the second function. Its derivative is 15x squared, plus the second function, 5x cubed minus 7, times the derivative of the first. Derivative of the first is 4x. Oh, not x. Sorry, this is x to the 1/2, right? Not x squared. I wrote that down wrong when I copied it. So you go back up. Yeah, that's 2x to the 1/2. So be sure you get that corrected on what I just did. So hit pause and make sure you correct that. And so that's 2x to the 1/2, not x squared. So its derivative then, because let me go back over this again. So I have first times the derivative of the second plus the second, and now I'm on times the derivative of the first. Well, the derivative of the first, the derivative of 3 is 0. 2 times a half is 1, and I'll have x to the negative 1/2. So this is the derivative of the first. So again, hit pause and go back if you're not sure about that and check what I did. All I did was move the power in front to do that derivative and lower the power 1. Now let me clean this up so we can see if it matches. So I need to distribute here on the left, so I get 45x squared plus 30x. I'm adding my powers, so 1/2 plus 2 would be 5 halves, plus, now I have 5x to the, well, it's 3 minus a half, So that's going to give me 6 halves minus 1 half is 5 halves minus 7x to the negative 1 half. Combining those two terms there in the middle, I have 45x squared plus 35x to the 5 halves minus 7x to the negative 1 half. If we look back, that's the same answer that I circled there. So everything checks. So the product rule, now, if you had this problem, I would say that it was much easier to do the first method. So when you have polynomials, a lot of times we don't really use the product rule. But definitely when we have trig functions and other things, we will use it. And then also when we have composition of functions later, you'll definitely want to use this. Okay, last thing we're going to learn, last thing we're going to learn is the quotient rule, and we'll go over the last page in class. So here we have the quotient rule. So this is how we handle if we're dividing. So the rule is for taking the derivative of u over v. Now I'm going to say it a little different. The paper has one way to say it. There are lots of ways to say it. I'm just going to use words. The rule is you're going to end up with another fraction. Bottom times derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Now some people will say this one is kind of like the one that's on the paper is kind of like Snow White and the Seven Dwarfs, so ho-de-hi minus hi-de-ho over ho squared. Most people I've heard it say low, okay, low being the bottom, low d-high, meaning derivative of the top, so low d-high minus high d-low over low squared. So that's more the way I hear it, so you can say it that way if you want, low d-high minus high d-low over low squared, or I will normally just say it in class in words. Bottom times derivative of the top minus the top times derivative of the bottom over the bottom squared. So let's go ahead and do these two examples, and then we'll talk about higher order derivatives in class. So this is example 14, and we have the derivative of x over x squared plus 1. So here we can't just make that into a power function. We have an actual quotient. And so we're going to find this derivative. So we're just going to follow the formula. It's really easy. So it is bottom times the derivative of the top, derivative of x is 1, minus the top times the derivative of the bottom, which would be 2x. All over the bottom squared. Do not multiply out the bottom ever, 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 ever. So the top is x squared plus 1 minus 2x squared over the bottom, which has been left alone, squared. And then x squared minus 2x squared is minus x squared plus 1 over the bottom, which is x squared plus 1 squared. Looks like something might cancel. It looks kind of good to you. You might look at it and go, oh, that's really close, but unfortunately close doesn't count. It's not exact. Nothing cancels there. Okay, last example, example 15. So we are taking the derivative of 5x squared over x cubed plus 1. So again, just say it in your head when you're doing it. It's bottom times the derivative of the top minus the top times the derivative of the bottom, all over bottom squared. Do not multiply out the bottom. Top you have to multiply out because we're trying to add terms, so we have to get it distributed. So we have 10x to the fourth plus 10x minus 15x to the fourth all over the bottom squared. So one last thing, we can just add those like terms. So we get negative 5x to the fourth plus 10x over x cubed plus 1 squared. And that's the answer, and we're done. Be sure you leave your denominators alone. Do not multiply them out. Numerator had to get multiplied in order to add terms, but the bottom should stay factored. All right, so that is it for what we're going to do for rules for differentiation, and we'll talk about higher order derivatives in class.